Hello, this is Nick Andre welcoming you to another screencast. In this screencast, we will study the Layer 3 of the OSI model and learn how it provides network services to end devices. This chapter describes the process the network layer uses to get segments started on their journey, and how packets arrive at their final destination. You will learn how Layer 3 divides networks into groups of hosts to manage the flow of data packets. We will also explore the routing process, that is the communication that occurs between networks. Let's recap. The application layer acts as an interface between the user and the networks used to conduct the conversation. The presentation layer converts the message of the conversation into data. When the transport layer receives the data, it breaks it down into segments. Now that these bits of data are processed into a transportable size and numbered for reliability, the network layer can deliver them. To accomplish this, the network layer encapsulates segments into packets. These new PDUs contain logical addresses used to describe how to relay the message. An intermediary device, like a router, uses this information to determine the best path to the final destination. In addition to this, the router also uses this information to direct messages along efficient and safely. Network layer protocols, such as the widely used Internet Protocol, are rules and instructions that devices use to describe the four tasks that make sharing of upper layer information between hosts possible. The next few slides will explain each task in more detail and describe popular network layer protocols that implement them. The first step, addressing, requires each packet to use some form of logical addressing scheme. The Internet Protocol requires each sending and receiving device to have a unique 32-bit address known as an IP address. The sender's address is stored in the source field of an IP packet, and it is used by the receiver to send data back. Of course, the address of the receiver is also stored in a field. The destination field, as it is appropriately called, is used by routers to calculate the best path for the packets to follow. As we well know, the process of adding information and creating a new PDU is called encapsulation. The second task, and the most common task for any network protocol, is to produce a new protocol data unit. The network layer adds a header to each segment. The IP header contains address information and some other bits that identify the PDU as a network layer PDU. When the transport layer PDU has been encapsulated at the network layer, it is referred to as a packet. The third task, routing, is the most important function of any network layer protocol. The routing process begins when a router determines the best path by using the address information stored in the received packet header. A router will forward this packet to the next appropriate router out of the interface that connects each router together. This process will continue until the packet arrives at a router who has an interface directly connected to the destination network. Each route that a packet takes to reach the next device is called a hop. During this, the addresses and segments are left alone until they reach their final destination. Decapsulation, the fourth and final responsibility of an OSI Layer 3 protocol, occurs only when the packet reaches its final destination, at which point the packet header is no longer useful and the end device will discard this information and pass the segment up the stack. A router, on the other hand, will only strip away the frame information to reveal the packet header. Now that the router has access to the packet header, it can use the addressing information to determine where to send the packet. The packet is then set back down the stack to be re-encapsulated and shipped out. In this section, we will explore IPv4, the most widely used network layer protocol. Here are a few examples of the network layer protocols. The most common and widely used protocol, soon to be replaced by IPv6, would be Internet Protocol version 4. We'll be focusing our attention on IPv4 in this course. In fact, Chapter 6 of Network Fundamentals is dedicated to this particular protocol. Network layer protocols describe services and structures that are used to encapsulate UDP datagrams or TCP segments handed down from the transport layer. In the case of IPv4, it was designed to produce very low overhead and to provide functions only necessary to deliver packets. Hence, IP must depend on upper layers to track and manage the flow of packets. Since IPv4 depends on these layers for reliable delivery, the destination is not contacted before a packet is sent. That is to say that IPv4 is connectionless, and it tries its best to get the message from one end device to the other. Not knowing whether the packet made it or not, IP must depend on TCP to handle reliability. Thus, it requires less data and uses much less processing power and bandwidth. One of the reasons why IPv4 is very popular has a lot to do with its flexible and open nature. Regardless of the media used to connect devices together, IP packets and their headers will remain the same. That is to say, a packet found on copper Ethernet will have the same header fields as a packet that floats across the airwaves. It is important to note that each media has its own maximum transmission capacity. This is known as a media's MTU. A router, as illustrated in this diagram, not only decides the path in which a packet takes, but it also acts as a bridge to connect different mediums together. Fragmentation happens when a router tries to pass packets onto a network medium that cannot handle the size of the packet. In other words, the packet size exceeds the MTU of the medium. Consequently, the router must break the packet up into smaller pieces called fragments. The next router will reassemble these fragments according to an offset number stored in the packet header. I mentioned earlier that a network layer protocol header stores addressing information used by routers to route packets along their way. In this particular diagram, we can see that IPv4 uses 32 bits to store the sender's address and another 32 bits to store the receiving host address. Other fields, like the time to live, TTL for short, have their own unique purpose. This particular field is used to describe the maximum hops a packet can travel before it is dropped. The protocol field uses 8 bits to indicate the transport layer protocol being used, like TCP or UDP. If a packet contains a ping message, then this field would be set to ICMP. We can also see the flag and fragment offset fields used by the routers to overcome mediums with smaller MTUs. In total, a typical packet consists of 24 bytes of data used for end-to-end delivery. Devices on a network can be grouped together to form logical networks, much like homes are grouped together to form neighborhoods. To identify these groups, an IPv4 address consists of two parts, the network address and the host address. The network portion of the address can tell a router where to find the neighborhood, and the host portion is used by the last router to find the house in that neighborhood. This type of addressing is considered to be hierarchical. Hierarchical addressing is read from the most general information to the most precise. The network portion of the address acts like a postal code and tells routers where to find the general neighborhood of a network. Routers forward packets between networks by referring only to the network part of the address. When the packet arrives at the last router, like a letter arriving at the last postal station, the local portion of the address will be used to identify the destination host. The portion of the address that is network and the portion that is host can vary. In this particular example, a network manager is using IPv4's flexibility to customize their private network by creating subnets. Subnets is the process of dividing larger networks into smaller networks. The green bits, in this case, represent the additional networking bits required for subnetting. Notice that these green bits are borrowed from the host portion of the address. Hence, the first 3 octets plus the green bits from the last octet would be used to represent the network portion of the address, and the black bits would represent the host part. We will explore this technique in another screencast. Computer communities are similar to human communities, in that as they grow, they become more complex, and at some point, dividing the larger network into smaller, more manageable groups can make sense. As communities and networks grow larger, they present problems that can be alleviated by dividing the network into smaller, interconnected networks. In growing computer networks, some common complications could arise, such as performance issues, security concerns, and host identification. To overcome these problems, a network administrator would have grouped computers geographically into smaller subnets, like city neighborhoods. Since workers with common tasks tend to work at a single location, administrators would group computers together by these locations. As networking technologies evolved, the nature of work groups began to change. Now network members can be grouped not just by physical attributes, but by abstract attributes such as purpose and ownership. Grouping hosts geographically was an economical way to improve performance by narrowing broadcasting to the physical location. A broadcast is a message sent from one host to all other hosts on the same network, and the purpose is usually to share its own information and to request information about others. ARPing would be an example of when devices are sharing information about themselves to other hosts. Hence, the more devices on the network, the more broadcasting. The more broadcasting, the more performance degrades. To overcome this problem, we divide networks into smaller interconnected networks. These smaller networks, also known as broadcast domains, are connected together by routers. In other words, routers divide networks into broadcast domains. In this particular illustration, we can see that each interface of the router represents a single broadcast domain. Dividing a network based on user access is an effective way to protect the organization's interest and employee privacy. Such access restrictions can be controlled by an intermediary device at the perimeter of the network. The firewall can be configured to allow only known, trusted data and users to access the network. In this illustration, we can see that both subnets have access to the internet. A device known as a firewall could be set up to allow or deny public access. The firewall, along with the router, is being used to protect information from common internet users while allowing access to the internet and to other subnets on the company's network. Routers act as postal workers at post offices for small networks by taking care of messages going out and serving as a general destination and sorting stations for messages coming in. In this section, we will explore how packets are delivered from end device to end device. Let's explore the routing process. In step 1, the sender determines the next device to receive the packet, either a local host or the default gateway. Step 2, encapsulates the packet into a frame and sends it out of the network interface card onto the switch. Depending on what the sender determined in step 1, the switch looks at the destination physical address stored in the frame and decides what port to send the frame out on. Using the netstat-r command, a network administrator can see the host routing table. Routing tables consist of 3 major components: the network destination address, next hop address, and the metrics. In this illustration, the gateway column would represent the next hop address. The packet will be passed to if the host can match the packet's destination network with an entry in the routing table. Any host configured with a default gateway address will contain a catch-all route known as the default route. That means any packet that wasn't matched with a better entry, the host will use the default route and pass the packet to the default gateway. Let's continue to explore the routing process. Step 3. If the physical address matches a local device, the switch relays the frame onto its final destination. Else, the switch forwards the frame to the default gateway. Routers process the packet at the network layer. In order to do this, the router first discards the data link encapsulation to examine the network portion of the destination address. With this information, the router checks the routing table for a match and forwards the packet out of the appropriate interface. Communication within a network or subnet happens without a network layer device. In other words, neighbors are able to communicate with each other without the need of a postal worker. When a host communicates outside the local network, a router acts as a gateway and performs the necessary functions to send a packet on its way. In this illustration, Before PC 192.168.2.30 can communicate with PC 192.168.3.4, both hosts must be properly configured with the respective gateway. That is to say, both the host IP address and the gateway address must have the same network address. In this case, PC 192.168.2.30 and gateway 192.168.2.1 belong to the same network, 192.168.2.0. The same is true about the other network. If the default gateway is configured incorrectly on the host can communicate with other hosts on the local network, but is unable to communicate with hosts on remote networks. Continuing with our example, step 4. For each packet that comes in, a router checks their routing table for a match. To forward a packet, a router requires a route to that network or a default route. Destination networks can be a number of hops away. Routers use routing tables to map packets to their destination. If a route does not exist on the router, it goes to the default route. If a default route is not configured, packets are dropped. Routing tables are used to determine the path packets will follow to reach its final destination. Depending on the contents of a router's routing table or a host routing table, a packet could be forward to the destination host if the destination network is directly connected to the router, or forward to the next hop router if no route exists for the destination and a default route is present, or forward to a default gateway if the originating host has a default gateway configured. Let's finish our example. When the router with the destination network address receives this packet, the router will pass it to the end device by way of an exit interface. Because of the hierarchical nature of IP addressing, a router's routing table can contain many routes. One route entry could reference a large network, and many others could point to that large network's subnets. Hence, there must be a precedence for the routers to follow. In this particular example, a packet destined to host 10.1.1.55 arrives at a router whose table could contain the following entries. A router will pick the route that matches the destination address the best. If the first entry does not appear in the table, then the router will pick the next best match. Notice the best match matches all 3 octets, where the second best match matches only 2 octets. If a router does not contain an entry that matches any of the octets, and it is configured with the default route, then the route will use this path to forward the packet. Else, the packet is dropped, and our router will be unable to deliver the message. A network administrator can teach a router new routes by manually configuring the router or by implementing a dynamic routing protocol like RIP. Information that is manually entered into the routing table is called a static route. Static routes are easy to install and use less overhead than dynamic routes. Unfortunately, static require manual updating as well. Hence, if the inter-network structure should change, local area networks may be without service until an administrator informs them of the new change. Dynamic routes help to overcome this limitation by providing routers with up-to-date routing tables without the need of an administrator. Routing protocols are the set of rules by which routers dynamically share their routing information. As routers become aware of changes to the networks for which they act as the gateway, or changes to links between other routers, the information is passed on to each other. The exchange of routing tables can consume additional bandwidth, and as a result, dynamic routing protocols are used in larger interconnected networks. Dynamic routing protocols also require additional processing and can be difficult for an administrator to troubleshoot and set up. Now that we have learned about routing theory, let's see it all in action. A host on network 192.168.12.0 wants to communicate with a host on the 172.16 network. So begins the routing process. The host determines that the receiver belongs to another network and it must pass the message to its network's default gateway. The gateway, router 1, strips the packet from the frame to reveal the message destination address. In this case, the message is meant for host 172.16.0.1. With this information, the router can calculate the receiver's network address and try to match this destination network address with an entry in its routing table. As we will see, the router will find a match. To reach the 172.16 network, this message must first travel to 192.168.0.2, the public side of router 2. Before the packet can be sent, router 1 must reframe the packet with the source MAC address of the interface that belongs to this public network and a destination MAC address of the 192.168.0.2. When the hub receives this message, it will send a copy of the message out of each port except the one the message came in on. Although this message was intended for router 2, the hub sent a copy to router 3. Router 3 decides to discard this message because its public interface MAC address does not match the MAC address inside the frame. While router 3 is discarding this message, router 2 is following the same steps that router 1 followed when the message arrived. Strip the packet from the frame, reveal the destination address, calculate the destination network address, find a match. In this case, the match router 2 finds does not contain a next hop address, but rather an exit interface. That is because router 2 is also the gateway for the 172.16 network. As a result, the router will reframe the message and send it to its final destination, 172.16.0.1. This was routing in action. This concludes Chapter 5, OSI Network Layer. In this chapter, we explored the role of the network layer, which is to encapsulate upper-level data into a packet and route it from one host to another, regardless of the type of data. The data is encapsulated into a packet. The packet header has fields that include the source and destination addresses of the packet. If a host creates a packet with the destination address outside the local network, the packet is sent to the default gateway for forwarding to the destination network. The default gateway is an interface of a router that is on the local network. The gateway router examines the destination address and, if it has knowledge of a route to the destination network, the packet is forwarded to either a connected network or to the next hop router. This is Nick Andre, and I will see you in the next screencast.